these lessons in English. I've been talking to Simon about how it went these days, and he mentioned that you thought that maybe it was a little bit tight in time. There is a lot of work to do, and maybe a few time to do it. I'm sorry to hear that. I will try to highlight what is most important, so you can focus on what is most important, and then you can also dedicate some times afterwards if you want to go deeply in this on all these concepts. Okay, so I hope that I can help you to prioritize what is most important, and I also hope that you find it interesting and you will to also discover all the rest of the things maybe after the lesson. Yeah, and we also talked yesterday that we will post the exam questions on Monday afternoon after the lecture, next lecture, which will be on Monday. Because if you have seen so let me present my screen. Yeah. So if you have seen here the program of this part of the course, you already did these three first lessons with Simon, and then today we are going to do the element technology lesson, and then on Monday we will do the frequency analysis and structural instability and backlink, and then on Tuesday there will be no recorded video lecture because it's what remains is the self-study lecture. But we will also have some time to comment on the notes because there will be no video lecture, but there will be some notes that are already available in Moodle that you can go through them, and then you will also have some time to ask questions in this regard. But to summarize, all the theoretical content of this course will be given on Monday, so that you will get the questions on Monday afternoon. Okay, and then we will also schedule exam question session such that you can go through the questions that will be posted, and then you will have the opportunity to ask about those questions to Sergey, Simon, and I in a session that we will schedule next week also. Okay, maybe on Wednesday, maybe on Thursday. We will post a news on Moodle telling you when it will be held. Okay. Okay. So did you watch the video? This time was a quite short video, so I hope that you had time to watch it. Did you do that?
Yes.
Okay. Okay. And how do you want to proceed? My idea is that I do a very brief recap. I go through the most important concepts of the video very quickly because I assume that you already have seen the video, but I just highlight the most important things. And then maybe we can start a discussion on some of the points there and also start discussing some of the questions that were posted in the video itself. And then after that, we will have some time for you to do the exercise that are proposed at the end of the notes. And I will be here to answer all your questions in regard to the exercises, okay? So here we have some self-evaluation questions that we can discuss after going through this recap. But before that, I would like to know if you had any questions with respect to the principle of minimum total potential energy that you did last lesson with Simon, and that you also had an exercise that was using it in order to obtain the stiffness matrix of a system made of two strings, like this one here. No, so you were asked to solve this system here and to find the stiffness matrix of this system by using the principle of total potential energy. Okay, did you reach to the solution?
More or less. I think we had trouble with the very last part about isolating P and
okay.
The matrix in itself.
So building the matrix itself. Okay.
Sorry?
So you know how to get the equations, but then from the equations to the matrix, so converting the equation into matrix form is in this step where you have some troubles.
Yeah.
Okay. So you, in the video, you also have these slides, so there is a brief explanation on how to obtain the equations, no? But I will go very quickly through them, just in case that some of you didn't reach to the point of getting the equations, okay? So you know that the total potential energy is the sum of the internal one and the external one. The internal one is basically the stored elastic energy by the strings, and it depends not on the movement or the displacement of these 2 points themselves, but it depends on the elongation of the string, okay? So this means that we cannot use directly the displacement of the nodes, but we have to think on how did this string elongate, no? So here, for instance, for string number 1, since this point on the left is fixed, we have that the displacement will be directly the displacement of point 1, right? So that's why we have here in this first part of the equation, we directly have the displacement of point 1. But this is not the case of the second string, because this string has moved the two extremes, no? The one on the left and the one on the right. So actually the elongation of this string is the rest, no, of U2 minus U1, no? So it's the displacement of this point 2 minus the displacement of this point 2, of this point 1, sorry. And then this equation you can expand it, no? Such that you have all these terms here, because here you have this term that can be expanded. And then for the external force potential energy, this is actually defined as the work that could be done, the maximum work that could be done, and is defined by an imaginary upper bonding, which we defined as H. You have to imagine that you have here an imaginary wall, and that means that this point cannot move further, this wall here, right? So the work that could be done by this force here is actually the product of the force by all this displacement. But which is the work that is actually done? So this force only did the work calculated by the product by P1 times the displacement of point 1. And which is the work that could be done by force P2? So this is the product of force P2 times this distance here, but which is the work that it was actually done by it? So it's the force P2 times the displacement of point 2. And in this way, we obtain the external force potential energy. And then the total one is the sum of these two, okay? And then, so here is just to have the same equation here in this slide. And then we need to find the derivative of this expression with respect to both, no? The displacement of point 1 and the displacement of point 2, because we need to do that for all the degrees of freedom of the system, okay? If we derivate this expression here with respect to displacement u1, we obtain this term here. And if we derivate it with respect to the displacement of point 2, we obtain this point here, okay? And then it's just a matter of converting these two equations into matrix form. To do that, we need to first isolate the forces. In this case, the forces are quite isolated, no? Because there is nothing that is multiplying them. So if you just pick this P1 here and move it into the right hand of this equation, you will have it isolated here. And then you can do the same for the second equation, no? This force here is not multiplied by anything else, so it's just a matter of translating it into the right-hand side of this equation. So then you will have the two forces already in the right side, okay? And then it's a matter of finding what is multiplying the displacement of point 1 and what is multiplying the displacement of point 2. In this case, from equation 1, we can see that multiplying the displacement of point 1, no? So here we have this product, K1 plus K2. So we write it here. And then multiplying the displacement of point 2, there's this minus K2. And how can we obtain from this matrix this equation here? So we need to multiply the first row by the displacement vector, no? And this is done multiplying this first term here by the first term in the vector of the displacement vector, and the second term here multiplied by the second term of the displacement vector. So if you do that, you will have K1 plus K2 times U1 minus K2 times U2. And that is equal, since this is the first row, is equal to the first position of this vector here. So this is equal to P1. And if we do the same from the second equation, we will have that multiplying U1, we have minus K2. So this needs to be written here. And then multiplying U2, we have K2. So this has to be written here. And how to obtain from this matrix form this equation, no? So then we multiply the second row by the displacement force, the displacement vector. And we will have the second position, since it is the second row, we will have the second position of the force vector. So we will have minus K2 times U1 plus K2 times U2 is equal to P2. So this is equivalent to this equation here.
Okay, that makes sense.
Okay. And then I guess that these questions, you already answered them with Simon. Did you have time to answer this question with Simon? Otherwise, we can very quickly comment them. So it was asked, the facility for listing reaction forces is used. Why is this a good way to check your model? So always checking the reaction forces is useful to check if the boundary conditions were correctly applied, because the reaction forces need to be always equal to the boundary conditions. And it's also useful to check if you applied the correct units. That it's a mistake that is usually done, because when you apply the boundary condition, sometimes you don't pay attention to the units, and maybe you want to apply, I don't know, you want to apply a displacement in millimeters, and you came up doing in meters, and you don't pay attention to that. So if you check the boundary conditions, the reaction force is a good way to check if you did it well in the definition. And then the assembly is made for several individual parts. Does the generated mesh account for this? Yes, it does. By default, all the parts that are touching together are meshed together. So they are sharing nodes. They are they are modeled as if they were bonded. Okay, they act together. And then in the video lecture, there was also some extra information making use of this simple model made of strings to do the analogy to a finite element model. Okay, so basically here what it explains is that the principle of the internal potential energy used in the string model can be also used to obtain the stiffness matrix of a finite element. Okay, in a finite element model. And here you can see that actually if you discretize a system of 3 finite elements, you will have that actually the stiffness matrix of each of them is always the same. So it's plus K3 minus K3 minus K3 plus K3. And then in the points where there is a shared node, the stiffness matrix are just add together. It's the sum over all the element stiffness matrix, as it says here. Okay. And I guess that you went through all this pseudo algorithm to obtain the stresses from the calculation of the displacement at the nodes. I will go through it very quickly also, just to make sure that this is clear. So how do we obtain, so which is the aim of doing a finite element analysis? So at this stage here where we are now is to obtain the stresses, and from these stresses we will compare them to the strength of the material, and then we will say, okay, if the computed stresses are higher than the strength of the material, no, the material property, then this component will fail. Okay, so basically we are designing a component, and this component is acting under some forces. Okay, and we want to figure out if it will be able to sustain all these forces. How do we do that? So we compute the stresses from a finite element model, and then from that stresses, no, we find the maximum one, and we compare it to the property of the material. If the stresses caused by this applied force are higher than the material property, it means that when we do it in reality, no, when we have this component built and we apply these forces on the component, it will fail. But if the stresses are lower, then we can more or less be sure that when we build this component and we apply some forces on it, it will carry these forces and it will not fail. Okay. And that if the calculation in finite elements was perfect and was accurate and exact, we will have this equation. No, we will try to make sure that the maximum stress is always lower than the material property. But since we assume that there will be some errors because what we are doing is a simplification of the reality, we apply a factor. Okay, just to be sure that it will never reach the maximum of the material property. So we say, okay, the maximum stress that this component should stand should be, so the maximum stress that we can have in this component in order for it not to fail should be, I don't know, 80% of the material property, just to be sure that we don't reach 100%. Okay, so this is to say that when we perform a finite element model, the information that we are seeking from it is the stresses. Okay, and how do we obtain the stresses? Okay, first of all, we do a CAD design of the model. No, we model the geometry of the component, and from that we generate the mesh. Generating the mesh means that we are going from an exact geometry to a geometry that is discretized into elements. Okay, this comes from the first lectures that you did with Simon. And when we generate this, once we have generated this mesh, we calculate the element stiffness matrices. For all the elements, we calculate their own stiffness matrix. And for the global model, we calculate the global stiffness matrix, which is nothing else but the sum of all the particular stiffness matrices of all the elements. Once we have that, we solve this equation here in order to have the nodal displacements. So we know the applied forces, we know the stiffness matrix because we calculate them, no, in step 2, and so by solving this equation we will obtain the nodal displacements. In order to know the displacements at any point of the model, we make use of the shape functions, which is nothing else than an equation that allows to interpolate the displacement inside the element. So we have the nodal displacements, and by making use of these interpolation functions, we will have the displacement at any point. If we derivate the shape functions, we will have the derivative of the displacement, and that is the strain. And by making use of the Hooke law, from strain, we can obtain the stresses. And we are done because, as we start discussing in this slide, what we were seeking was the stresses. So we reach this point. Okay. Do you have any other question from last lecture? So do you have any question in regard to all these concepts presented here? Okay, so I guess that silent means no. So let's start with the topic of today. Today we will see different element technologies, okay? Basically, we will see 3 types of elements: the solid ones, the beam ones, and the shell ones, okay? Let's start by the solid ones, which are the ones that you already saw, okay? The solid ones make no simplifications in terms of the degrees of freedom. So the solid ones is the one that you have seen until now. So you have a complex geometry, no, that comes from reality, and that geometry you split it into different elements, and each of these elements is what we call a solid element, okay? If we perform a 1D simulation, we will have only 1 degree of freedom per node. So for instance, if we had this element here, this element can only move, this node can only move in this direction, and this node can only move in this direction, because we are in a 1-dimensional simulation. If we are in a 2-dimensional simulation, we will have 2 degrees of freedom per node. In this case, will be the horizontal and the vertical direction, no? And this for each of the nodes of the element. And if we are in a 3D simulation, we will have 3 degrees of freedom per node. So this means that no dimensional simplification is made, okay? So depending on the dimensions of our simulation, we will have 1, 2, or 3 degrees of freedom. But there are some kinds of elements that are used to improve the efficiency of the models. And this is done by including some extra degrees of freedom. For instance, we have these stress elements that can only sustain axial load. They can only be compressed or tensioned, but they cannot bend, okay, or any other movement that is not aligned with the axial direction. Then we have these two kind of elements that are based on simulating the neutral axis, in this case of the beam, or the midplane of the model. Okay, so we are reducing all this geometry that is in 3 dimensions into, in this case, 2 dimensions, or 1 dimension or 2 dimensions. So basically the trick here is that we are converting what is a beam into a line and what is a plate into a surface. And this is very efficient in terms of computation, okay? Because if we had to model this into solid elements, we would have to use a lot of elements. See, for instance, in this previous slide, if we wanted to model this beam, count here how many elements we would need. We would need, I don't know, let's say 100 elements, while here with 5 elements, it's enough to obtain the exact same results, okay? Okay, so in the slides, there was proposed this exercise here, where you were asked to say how many degrees of freedom have all these cases here. Can any one of you tell me how many degrees of freedom we have here, for instance, in case A?
4.
4. Okay. Since we have 2 nodes, we have 2 degrees of freedom per node. Okay, you answered 4 because you are assuming that this is which kind of element you are assuming that it is?
A solid.
Okay, so if it is a solid element in 2 dimensions, it means that we have 2 degrees of freedom per node, as you said, and these 2 degrees of freedom would be the horizontal displacement and the vertical displacement. Okay, and that is perfectly correct. There was another possibility, and it is that you assume that it was actually a beam element. If it was a beam element, you would have also 2 degrees of freedom, but it will be different. They will be different. There will be the vertical displacement plus the rotation, no, in this direction here. But both answers well correct. Okay. Did you have any trouble on figuring out how many degrees of freedom had any of these cases? Do you want to comment any of these cases in particular?
Yeah, I have one.
Okay.
H in 3D.
So this one here.
Yeah, because in the slides it says 4 degrees of freedom, but when I look it up on the internet, it says 6 degrees of freedom. It has 3 in the translational direction and then 3 in the rotational direction.
Yeah.
If it's a beam.
Yeah. And this depends on how we define a beam. Okay? If we define a beam as it is defined here, what we call here beam elements, then it's true that it has 4 degrees of freedom, because we have this displacement here, okay, the vertical displacement, then the displacement that would go outside the screen, okay, so in this direction here, and then we have the 2 rotations, no, with respect to these 2 axes. But if we sum beam plus truss, having what we call here frame element, let me look for it. Okay, so here we call frame elements the summation of a truss element or a bar element and a beam element. So we have, for instance, in 2 dimensions, we have these 2 degrees of freedom plus these 2 other degrees of freedom, okay? So we are allowing not only to apply vertical displacement, but also to deform in the axial direction, okay? And in 3 dimensions, this is translated into this. So we here have 6 degrees of freedom. We have the 4 degrees of freedom that come from our definition of beam elements plus the axial deformation and the torsion, okay? And this is called in SolidWorks as beam, okay? So it is a little bit confusing, but it is also noted here, okay? So what we call frame elements, which is the summation of truss elements plus beam elements, is called in SolidWorks beam elements, okay? So this means that your question was right. And it depends on how do you define beam elements. If you look it into the internet, you must probably find that beam elements are these ones here, no? According to the nomenclature of SolidWorks. But if you use the definition of beam elements from these notes, you would have to answer that it only has 4 degrees of freedom. Is it more or less clear?
Yeah, more or less.
Okay. So. Yeah. Okay, perfect. So it's a confusion with the way to call the different elements, okay? You just need to have clear that what we call beam elements does not account for axial displacement, okay? So what we call beam elements only accounts for vertical displacement and moments, okay? Bending moments. But in SolidWorks, what it is a beam element is an element that is capable to sustain bending moments and vertical displacement plus axial displacement and torsion, okay? So it has 6 degrees of freedom. Okay. Basically, here we present again beam and shell elements just to mention the most important feature of these elements. No, the main trick here is that we are actually solving a 3D problem by reducing it into, in the case of beam elements, into a line, and in the case of shell elements, into a surface. So we know that it's a volume, okay, but we will calculate everything to the middle plane, and then from the results on the middle plane, we will calculate the displacements, the strains, and the stresses at the other points of the solid, okay? And this reduces a lot the computational time, okay? Because we only need to solve a problem that is reduced into a line or a surface. How is this done? Okay, this is done by applying what is called Euler-Bernoulli theory, and it is based on this theoretical explanation here, okay? This is for you to know where these equations come from. It's not essential that you memorize all this theoretical explanation, okay? So basically what I'm saying here is that you will not be asked to do all this development here, okay? Of course, it's very nice and is always more gratifying for you to know where all these things come from, and for you to see that it's not magic what is done here, okay? So everything that is done has an explanation behind. But what I'm saying here is that you don't have to memorize all this development here, okay? You will not be asked for that, okay? But I just want to make sure that you actually can see where all these simplifications come from, okay? But so the important thing here to know, no, not to memorize, but to understand, is that the strains, no? So we are again at the same point, right? So we are here calculating the stresses. We are always interested on obtaining the stresses, okay? And for then compare them to the material properties, okay? So how do we obtain the stresses? So again, from Hooke law, no? So we need to obtain the strains. And how are the strains obtained here? So before they were obtained directly from the derivative of the displacement, okay? But in this case, we have to calculate the double derivative of the displacement, okay? And it will also depend on the coordinate with respect to the neutral axis, okay? And here there is again a quite long demonstration on how is obtained the stiffness matrix of a beam element, okay? There are two ways to do that. The first way is the first way presented here, where we say, okay, we have this beam element where there are 4 degrees of freedom, not 2 per node. We have the displacement and the rotation at node 1 and the displacement and the rotation at node 2. So we have 4 degrees of freedom. So it means that here in the displacement vector, we will have to have 4 spaces, okay? And then how many forces can we apply to this element? We can apply a force and a moment at node 1, which are these 2, and a force and a moment at node 2, which are these 2 here. So we now know that the stiffness matrix will be a matrix 4 times 4, okay? So we need to obtain in total 16 coefficients, no, of this matrix. How do we do that? Okay, so the first way to do that is to assume that this beam actually we only apply a displacement at node 1. If we only apply a displacement at node 1 and we keep all the rest of degrees of freedoms to 0, we will have that the vector of degrees of freedom is this one here, 1, 0, 0, 0, because only the displacement is different from 0. We can do a second case where instead of a displacement, we apply a rotation. So in this case, the displacement vector will be 0, 1, 0, 0, and the same for node 2. So for instance, for this case, for case 1, where we only have a displacement applied at node 1, we will have that this equation here, no? So we take this vector here and we substitute it by this one here. And this means that all this part of the matrix doesn't account, and we only make use of the first column of the stiffness matrix. So this means that F1, M1, F2, and M2 will be the product of this vector here by this vector here. So means that K11 will be equal to force 1, and so on. From mechanics of materials, we can obtain so we can obtain the solution for this case here. So in order to obtain a displacement at this extreme here, and any rotation and any displacement at this point here, It's the same as having a beam encasted at this side here, okay? And we can apply a force and a moment to obtain this displacement here, but we know that the rotation must be 0. So we have from mechanics of materials this solution here, and we know that the sum of this and this should be 0. Sorry, this and this term here plus this term here should be 0 because the angle is 0, and this term here plus this term here should be 1 because we applied a unit displacement. If we solve that, we will obtain the two first coefficients of the stiffness matrix, and then by equilibrium of forces and moments, we will obtain the other two coefficients of the stiffness matrix. And finally, we will have solved the first column of the stiffness matrix. And then by making use of the other three cases here, so with this case here, we will solve these coefficients here. With this case here, we will solve these coefficients here. And with this case, we will solve these coefficients. Quite long way to obtain the stiffness matrix of a beam element, okay? But anyways, it's long, but it works, and with that we obtain the stiffness matrix of a beam element, and then if we substitute for a real case where, for instance, we can have a quadrilateral section of 10 times 10 and a length of 100 millimeters, we will obtain these results here. And if you do that also in SolidWorks, you will obtain very similar results. You have a video in Moodle where this exercise is solved, okay, in SolidWorks. If you follow the video, you don't have to do it yourself. But if you watch very quickly the video, which is very short, it's few minutes long, you will see that the results are very similar to the ones that we obtain manually, okay? You can see here that there is approximately 3% of error between the solution that we obtain manually and the solution from SolidWorks. Okay, for instance, here in SolidWorks, we have that the reaction force in Y is 2.04, and here is 2.1, okay? This is because in SolidWorks, there are so the theory behind in SolidWorks is not as simple as the one that we describe here, but it also includes an extra formulation in order to account for the rotation of the cross sections, okay? And with our theory here explained here, we assume that the cross sections remain plane. And this leads to this very low error when you compare both results. Okay, again, you don't need to know all this derivation here. So you will not be asked to obtain the stiffness matrix of a beam element by using all these cases here from mechanics of materials, okay? But what you will be asked is what is asked in the self-evaluation questions. That is, for instance, which are the basic ingredients used in the derivation of the stiffness matrix of a beam element, okay? So you don't have to know all this development, but for instance, you have to know that in the stiffness matrix, you have the Young modulus, you have the moment of inertia, and you have the length of the beam element, okay? Another way, well, before that, just a brief mention to which kind of shape functions do we need to use for a beam element. In this case, we need to use a third order shape functions. Why we need to use that? Because if we look at the solution from mechanics of materials of the displacement along the coordinate x, we will see that the displacement is actually a third order degree, okay? So if we use a shape function that is a degree lower than 3, we don't have a correct representation of the displacement along the length of the beam, okay? That's why we need to use a third order degree shape function. Do you more or less understand that? So remember, from the finite element model, we solve the displacements at the nodes, okay? So then, if we want to know the displacement at a point inside the element, no? Imagine, after solving the equation of the stiffness matrix times the displacement is equal to the force, we will have the displacement at this point here and at this point here, okay? So the nodal displacement. But then imagine that we want to know the displacement at a point inside the element, for instance, here, okay? For making that, we interpolate using the shape functions. If the shape functions are lower than a third degree, sorry, for instance, if we use second degree shape functions, the interpolation of the displacement inside the element will be a second degree equation. So we will see that the displacement vary linearly inside the element, okay? So instead of this shape here, which is the real shape, we will see that the element varies linearly. And that will not represent the reality. So in order to have a displacement inside the beam element like this, curved like this, we need to use a third degree shape function. Okay? Okay. So, and then remember that for a solid element, we derived the expression to obtain the stiffness matrix, which was this expression here. Okay, this came from the principle of minimal total potential energy. Okay, remember that the stiffness matrix was calculated with this expression here. This is nothing else but the derivative of the shape functions times the Young modulus times the derivative of the shape functions. Okay, and that is integrated over the volume of the element. But this was for a solid element because the derivative of the shape functions times the nodal displacement was giving the strain. So let me recover that slide. Here. Okay, so we have that the displacement at any point inside the element is the shape functions times the nodal displacement. And for the strain, which is the derivative of the displacement, we have that the derivative of the shape functions times the nodal displacement is equal to the strain, okay? If we group these terms here, so if we take the derivative of the shape function, we obtain what we call the B matrix, okay? Remember this, that the strains are the derivative of the displacements. In the case of, that is for a solid element, but in the case of a beam element, we have here that the strains are minus the coordinate from the neutral axis times the curvature. And the curvature is the second derivative of the vertical displacement. So this means that actually the strains here are not the derivative of the displacement, but they are the double derivative of the displacement. Okay, so this means that in this case, we don't have a B matrix as defined previously as the derivative of the shape functions, but we have that what we call B star is minus the coordinate with respect to the neutral axis times the double derivative of the shape functions. Okay? So this means that to obtain the stiffness matrix, we need to solve this integral here. That is actually this one here, because if we have here z multiplying, that if we group, we have a square z, and the integral of a square z over the area is what we call the moment of inertia. So this is how we come from this step here to this one here, okay? And if we solve this integral, we obtain the same stiffness matrix as we obtained previously by doing this derivation here, okay? But this is not easy to do manually, so this is why you have how it is derived by making use of Maple. So a calculation, a math program, okay? If you had to do it manually, it would take some time. But again, this is not the main topic here, okay? The main topic here is to remember that the key ingredients in obtaining the stiffness matrix is, again, the Young modulus, the moment of inertia, the length of the beam element, and you can also see that it is very important the kind of shape functions that we use, okay? So a key point, again, is to remember that when using beam elements, we need to use third-degree shape functions. Otherwise, we don't have the proper representation of the displacement along the length of the beam element, okay? So these are the key concepts here. It's not actually important going through all this integral here, which can finally be solved by using a mathematical program, but what is important is to remember to use the proper shape functions, okay? And that these are the key ingredients that are used to build the stiffness matrix. Okay, then we talk about truss elements, that are those ones that can only support axial deformations, okay, so they can only be compressed or tensioned. And as we said before, frame elements are the sum of beam elements and truss elements. So we take the beam elements which can support bending moment and vertical displacement, and then we add the capacity of the truss elements to be deformed in the axial direction. Okay, here you finally have some tricks to get simulations of all these kind of elements in SolidWorks. And you will go through all these tricks when you do the tutorials, okay? You are proposed at the end of this lecture to do some tutorials, and in these tutorials you will make use of all these tricks, okay? And additionally, you have a video posted in Moodle where you can see this example of a shared model by shell elements, okay? It's also modeled using solid elements, which is a bad approach, because for obtaining the same results, you use a lot more elements, and in consequence, you use also a lot more of computational time. So you can see a video of this exercise. You are not supposed to do this exercise again by yourself, but you can watch the video and see which is the implications of using solid elements versus using shell elements, and how much more efficient is using shell elements. Okay. What time is it? Okay. We spent 1 hour going through the main concepts of this lecture. And now you have some time to do these exercises, okay? you can start by using a tutorial about truss structures, these ones that can be only deformed actually in the axial direction. You also have a tutorial about beam diagrams, okay, using beam elements. That is what we call here FEM elements, remember? And then after this completion of these two tutorials, you can answer these questions. You can do it in groups. Then you can solve this problem, which you have in the appendix the solution calculated analytically by hand, and you can compare the solution from mechanics of materials with the solution obtained in SolidWorks. Okay, and finally, you can also do the tutorial about the shell elements. Okay, and after that, you can try to answer these questions. Is there any question before you start with the exercise?
I have a question.
Yeah.
Will we go through the self-evaluation questions?
Yes. Do you want to do that now?
We've just done that in the previous lectures.
Okay, let's do that then. I think it's very important to go through the self-evaluation questions because they are more similar to what you will be asked in the exam. Okay, so it's a way to make sure of what you need to learn from this lecture. Okay. Okay. So the first one says classify different element types and describe their weaknesses and benefits. Does any of you want to answer this question? Okay, well, in this case, we can make use of this is like here, just to list the three kind of elements that we can find. Okay, we can find, well, four kind. We can find solid elements which have no simplifications in terms of dimensional simplifications. So they will have as many degrees of freedom as dimensions in the simulation. Okay, and then we have these different technology elements that the main feature of them is that they reduce, no, so for instance, for beam elements, no, in order to simulate a beam which is a solid in 3 dimensions, we only make use of a line, okay, and we solve all the displacements in the line, and once we have that, making use of the formulas that we have seen, we can find the displacement at any point in the beam, okay? The same for the shells. They are simulating a solid, but only making use of a surface. So we solve the problem at the surface, we find all the displacements at the surface, and once we have that, making use of a formulation, we can extrapolate from the displacements at the surface into the displacement at any point in the solid. So this means that instead of solving a complete solid, we just need to solve a surface. And you can imagine that it is much more efficient than solving all the solid, okay? So these were basically the kind of elements that we can find. And the weaknesses and benefits of all of them is that in case of the solids, they don't make use of any simplification, but they are very the computational cost is very high, okay? In the case of truss, beam, and shell elements, they are much more efficient, but we need to be conscious that they are simplifications, okay? So we need to make sure that we are taking into account all, for instance, in the beam element, okay? We are solving the displacement at the neutral line, okay? And we will see that. But then we have two upper limits, okay? You know that the bending stresses, where they are more high, are at the top or at the bottom, okay? So then, when we plot the results, we have to make sure that we check both, that we check the stresses at the upper limit and the stresses at the lower limit, because the maximum can be either on the top or on the bottom, okay? Since we are only solving the neutral line, we have to be conscious that the maximum can be either on the top or on the bottom, and we have to check both, okay? You will see, if you go through the tutorial, that in SolidWorks, there's a way to represent the stresses that it automatically selects the one that is higher, okay? And you will also have the possibility to plot the stresses all through the section, such that you can see both the top part and the bottom part at the same time, and then you visually see which is higher, okay? For the shell element is the same, okay? You solve the problem at the mid plane, okay? But the maximum can be either on the top or on the bottom. So you need to represent both on the top and on the bottom to see what is the maximum, okay? Describe the basic ingredients involved in obtaining a formulation for a beam element stiffness matrix. We actually went through this, and I did a lot of emphasis on what it is important here, okay? Note that here in the question, it doesn't say, okay, do the development of all the stiffness matrix. That's not the question here. The question is the basic ingredients, okay? And we already went through them. It is the Young modulus, the moment of inertia, and the length of the beam element. And also it's very important because it's inside the derivation of the stiffness matrix, which kind of shape functions do we use. If we use a degree that is lower than 3, we will not have a good representation of the displacement along the beam element, okay? And then describe how to plot the results of truss, beams, and shell respectively. You will see that through the tutorials, okay? And you also have some notes in the last slides. But here, again, what is important is to have in mind what I told you in question 1, okay? So it is always important to visualize both extremes, the upper one and the lower one, because we never know where will be the maximum stress, okay? So this is what we should be careful about. To always make sure that we are visualizing the extreme, either the top one or the bottom one, where the maximum stress is, okay? Okay, so if you don't have any other question, you can start with the exercises, and I will be here in the main team, and if any of you has any question, you just invite me to join your group teams. Is it okay with you?
Yes.
Okay.
Yeah.